We're doing a bunch of magnetic odds and ends in this video, so the next thing is magnetic materials. Let's talk about them. They work a lot like dielectrics, except because magnetic fields come from currents, magnetic materials happen when there are charges moving around inside your material. So imagine, for the sake of argument, that you have an electron that is orbiting a nucleus. We know that that's not really what atoms look like, and in general, electrons are more in a cloud, probabilistically, around the nucleus. But you can imagine that that cloud might have a net rotation and a net current inside of its randomness that is not zero. And its net current might lead to some rotational current like that, even though really the electrons are kind of probabilistically all over the place. So these molecules have an internal magnetization, because remember, if you have a loop of current, you end up with a magnetic field that sort of looks like this, passing through the current, passing through the loop. And it's not lopsided. That looks pretty good. So these molecules, because they have basically a loop of current, because their electrons are on average moving, they have an internal magnetization, which is analogous to the polarization vector for dielectric materials. So this magnetization vector is equal to chi m, the magnetic susceptibility, times the magnetic field. Because of that, your magnetic flux density is mu naught times, oh, and the reason that this is true is because all of these magnetic fields that are generated by the internal particles, in general, they point every which way. But when a magnetic field is applied, they all line up and they agree in direction. And that is what causes this next thing to happen. So our magnetic flux density is increased by this thing. So then we have mu naught 1 plus chi m times h, which we usually write as mu naught times mu r, the relative permeability, times h. And just like we saw with electric fields and dielectric materials, if you have a situation where B stays the same, obviously that would mean that H decreases. So if you have a certain amount of magnetic flux and its flux lines pass through a material with high mu, that means that B has to stay the same to keep the magnetic flux the same. Because of that normal magnetic field boundary condition, remember? N dot B2 minus B1 equals 0. And when this is the case, that means that increasing mu decreases H. Other times, you have a situation where your magnetic field is generated by a current, and Ampere's law doesn't depend on mu, so then increasing mu just increases B inside the material. Fundamentally, it kind of turns out to be the same thing in the end. Speaking of Ampere's law and boundary conditions, another magnetic odds and ends type thing that we are going to do in this video is we're going to talk about a tangential boundary condition for magnetic fields. So consider the situation now. Now that we've talked about magnetic materials, let's say we have two magnetic materials, mu2 on the top, mu1 on the bottom, a surface normal vector that points from material 1 into material 2, as it always does. And let's define an Amperian loop here. And we're going to let its height go to 0. So then if we do our Ampere's law application, we are going to be taking the limit as the height goes to 0 of closed loop integral of h dot dl, which has got to be equal to the limit as the height goes to 0 of the current flowing through the surface. And I'm going to include the time derivative of the electric flux, but then I'm going to tell you that it is equal to 0. Because, here's the reason that it's equal to 0. If we let the height go to 0, then there won't be any area for the flux to go through. So, nothing there. On the other hand, this one is not 0 because we can have a surface current. So, what we end up with here is we've got h dot dl. Here's h2. Let's say it's going that way. And here's h1 going that way. Except dl is pointing in opposite directions on either side of this. So this integral of h dot dl turns out to be the integral from, let's say, 0 to delta L of h2 minus h1 dl. Yeah, that can be dl. We haven't really defined a coordinate system here. And on the other side, we end up with the integral from 0 to delta L of, now this ds, this does not point in the surface normal vector direction, it points into the board the way I've drawn it. So it's lying on the surface. So k dot ds that way, which is just going to be kdl. So in order for this to be true, no matter where we choose it, this stuff has to be equal everywhere. So at the end, what we end up with is that the surface normal vector cross product with h2 minus h1 is equal to the surface current density on the interface between the two materials. Meaning that if your two materials are not conductive and there is no surface current there, then these things have to add up to 0. An important thing to note here is that this surface current is not in the same direction as the magnetic fields because of this cross product. So the magnetic fields are pointing to the right, or they're pointing to the left or something, and K is pointing into or out of the board. One last topic to talk about in this kind of all over the place video is the idea of magnetic circuits. Magnetic circuits are a thing because, like current, magnetic flux only ever goes in a loop. Right? Your magnetic field lines, because B and H are solenoidal, your magnetic field lines always go like this. And since we have magnetic materials now that confine magnetic fields, by magnetic materials I mean things with high values of permeability, mu. What that means is that the flux really wants to stay inside that material as long as it provides a closed path. So if I draw something that is vaguely loop-shaped and I assign it a high value of mu, my magnetic fields are going to stay inside there. And if I draw some loops of current around this magnetic material, like that, and I allow it to carry that current I, then this current I acts as a source for some amount of magnetic flux. We can find out how much magnetic flux there is, and then we can talk about what is going on inside of this magnetic circuit. We can also have two different values of mu r, like we can split it up like this, and this could be mu 1, and this part could be mu 2. Then, if all of the magnetic flux is confined inside of this magnetic material, and we assume that the magnetic flux density B is uniform across the cross-section of the magnetic core, and that the magnetic field intensity H is the same lengthwise along one of these segments, although it can be different when you change materials and stuff. Then applying Ampere's circuit law around this loop, notice that we have two different values of H, right? We've got H in material 1, we've got H in material 2. So then we end up with integral from, let's say, 0 to L1 of H1 dot dl plus integral from L1 to L2 of H2 dot dl. Well, L2 plus L1, right, for the total length. So then we got H1, L1, and that whole thing has to add up to the amount of current going through the surface. Cool, so H1, L1 plus H2, L2 is Ni. Now we're going to define a new thing called the magnetomotive force, which is which for each of these segments is just H times L. Right, so this is the MMF, magnetomotive force, for each of the segments. We use a fancy letter F for that. It's a little bit hard to write, but we're going to write it like this. Good enough. And these magnetomotive forces have to add up to the total magnetomotive force, which is this one. If this is looking to you a little bit like Kirchhoff's voltage law, you are right. This is why we call them magnetic circuits. We also know that the magnetic flux in each of these segments has to be the same because magnetic flux is solenoidal, so if it's entirely contained in the core, it can't be having its field lines start and end willy-nilly. It just doesn't do that. So it has to stay constant all the way around because there's nowhere literally for it to go. So we have, knowing that, we know that flux 1 is equal to flux 2, which is, here we're going to have B1 times the area for flux 1, and in flux 2 we're going to have B2 times the area. The areas are the same, and the B's are the same because the fluxes are the same, which means that the H's are not the same. Right? So we can express H1 in terms of this as flux, right? Because we have the same total flux everywhere, we're just going to write it as flux, divided by mu naught mu 1 times the area. So that's H1. And we can write a similar thing for H2 is flux divided, that's not a flux, flux divided by mu naught mu 2 times the area. These are relative permeabilities, which is why I'm including mu naught in these expressions. So then we can rewrite this magnetomotive force equation as flux times L over mu naught mu1a plus L over mu naught mu2a is equal to Ni. Now this looks a lot like the resistance of something, right? Remember, the expression we came up with for the resistance of something was also the length divided by the cross-sectional area times submaterial parameters. This, in a magnetic circuit, is equivalent to a resistance, but we call it a reluctance. And the reason we care about this, and it has a fancy R as its symbol, with a little loop R like that. It's best I can do. The reluctance tells you how much current is needed to produce the amount of magnetic flux that you want. So if you know the reluctance of a circuit, you can figure out how much current is needed to produce the amount of flux that you would like there. This kind of question of magnetic circuits and reluctance and the amount of flux that you want and the amount of current that's required to produce that flux becomes relevant when we start talking about applications of magnetic circuits, like, for instance, electric motors.